Hey, welcome everyone to another session of online causal inference seminar. Today's format is a young researchers seminar format where we would have two speakers. Each would have about 25 to 30 minutes, allowing for a Q&A. And our first speaker is Drago Plečko from Columbia University, talking about monotonicity in graphical causal models and algorithmic approach. And our second speaker is Daiqi from Harvard University, talking about harnessing causality in online reinforcement learning for digital interventions. Today's Q&A will be handled by Sarah, so I'll pass the mic to her.
Thank you, Razi. This is just to remind you to please use the Q&A. And we will, I will read actually the Q&A questions out loud at the end of the talks, and then the speakers will answer them. So please use the Q&A function. So now, without further ado, I will leave the floor to Drago.
Right. Good. Thank you. First of all, thanks for the invitation. It's very nice to be here and be speaking about our work on monotonicity. So my name is Drago. I'm currently a postdoc in Columbia Computer Science in the Causal AI lab, working with Professor Elias Barenboim. So I want to share 2 pointers before I begin. So there are two sort of technical reports that you can look at. First is a technical note, which is very related to the presentation today. And the second is the full paper that came out in AAAI this year that has all of the formal results on monotonicity. Okay. Good. So the first thing that I want to discuss, I want to put a bit of context on the topic that we're studying and mention why we're trying to study this and what is the sort of bigger picture behind all of this. And what I want to start with, this very familiar notion to a lot of people studying causal inference of identifying causal effects. And what I'm going to talk about, the what I call an identification spectrum and different types of classes of problems that exist in identification. So what I'm going to start with, non-parametric identification, which is a setting in which we avoid any assumption on the functional mechanisms that we have, right? We're trying to place no functional assumptions at all and perform causal effects and identification in this setting, right? And there are some famous methods that have been developed over the years for this specific setting. One very well-known method that allows for identification of causal effects in a non-parametric setting is conditional ignorability, right? Starting in the 70s, and there have been many additional methods related to conditional ignorability, extending this in different settings. One worth mentioning is the backdoor criterion developed by Judea Pearl, and of course further graphical extensions of this have been developed as well. For example, the front door criterion falls under this umbrella as well, and generally the rules of do calculus developed in the 90s, they can also be thought of as tools for allowing for non-parametric identification. Finally, nowadays, we know that we have complete algorithms, right? We have several complete algorithms for identification of causal effects in this non-parametric identification setting. So that's great. So this problem has been to a large degree closed. Many of the results are known. There are interesting estimation questions still, but the point of this talk is not to go into estimation. We're going to be talking mainly about identification. Now, on the opposite end of this spectrum, we have this setting in which we are placing as many assumptions, the strongest assumptions possible, right, on our functional mechanisms. And here I specifically want to mention the linear Gaussian identification case, right? So in this setting, one of the first methods going back even to Gauss, I guess end of the 18th century, is just causal regression, right? So if we regress things properly and the mechanisms are linear, we can recover causal effects in a very simple way, right? In the 50s, in the econometrics literature, extensions of this for very interesting cases, such as instrumental variables, have been developed, right? So this is another tool that you can think of for linear identification. Beyond this, there has been a lot of work actually on this topic in the graphical side, in the graphical literature on causal inference. So people have developed this methodology of instrumental sets. People have developed auxiliary variables, and finally half-tracks, right? These are a couple of methods that are very powerful for linear effect identification. And actually, this question is almost closed. So actually, there's an algorithm that can recover that is complete, but it is actually like very slow computationally. But what I'm trying to convey is there's a lot of work in linear Gaussian identification on the other end of this spectrum. Now, the question is, what is in between, right? And have the topics in between been studied well? And is there anything that we can do? And what I want to mention, there are some topics that are in between which have been well studied. For example, additive additive noise models. So people have studied additive noise models, but what we really want to focus on in this talk, we want to talk about shape constraint identification, and in particular monotonicity in our context. And then there is a seed, like previously, there's a very well-known result from 1995 from Angrist and Imbens, and the latter author is actually one of the organizers of the online causal inference seminar. So there's this notion of using monotonicity to estimate local average treatment effects, right? So this is one of the key results that shows that we can use monotonicity to improve causal effect identification. So in this talk, what we're going to do is we're going to try to extend these ideas of using monotonicity and create an algorithmic approach for doing so, right? This is our whole goal. And before I go into the algorithmic approach, I just want to recover this setting of local average treatment effects, or LATE. And I just want to give you an example for those in the audience who may not be familiar with this. And I guess these results are really well known, but I will just recap them for the completeness of the talk. So what we're trying to do, and I'll start with an example. So what we're trying to analyze an outcome which could be job performance or a salary or something along these lines. And we're interested in whether participation in a job training program improves performance or the salary of the individual. Right, and so treatment X participation is right. Treatment is labeled X, and the outcome is labeled Y. In this setting, what we have access to an instrument which tells us whether the person was invited to a job training program. Right, so it's not participation but an invitation. So what this gives us, it gives us this graph on the right. So Z is pointing to X and X is pointing to Y. Crucially, there could be unobserved confounders between X and Y, right, that we don't have access to. And what we would ideally want, we want to estimate some kind of a causal effect from X to Y in this IV setting. Now, the first result that we can mention, we can look at the average treatment effect, the ATE. So in my notation, subscript denotes the potential outcome. So this is a potential outcome of Y, subscript X, if we were setting X to be equal to 1 versus setting X to be equal to 0, right? So with the first result that is negative is that in this setting, in the fairly general setting, we cannot identify this average treatment effect, right? This is not doable. Now, what is sort of nice and what is the result of Angrist and Imbens from 95 is that actually for a subgroup of the population, this can actually be identified. And there's a specific subgroup that we will condition on for which the total effect can be identified, right? And this subgroup is usually referred to as the compliers group. So what that means, it means that the potential outcome, if we set Z to 0 of X equals 0, whereas if we set Z to 1, X equals 1, right? So what this means is that if people are, for these individuals, if people are invited to the job training program, they will actually attend, but if they're not invited, they will not attend, right? So this is the group of individuals. And now the key result is that this actually effect is identifiable, but we need an additional assumption. And this assumption is that the effect of Z on X is actually monotonic. And by monotonic, what we mean is that if we change Z from 0 to 1, it can only increase the value of X, right? So as I mentioned previously, this is where this result first appears in the literature. Now, I want to roughly go and just to conclude, right? So what we see here is that under monotonicity, actually queries that are actually non-identifiable in general can become identifiable, right? Which is very useful. So these shape constraints can help identification. Now, what I want to go through quickly, just to give you an idea of what is used in this proof, I just want to recap the proof of local average treatment effects. So how do we show this? And this proof is actually quite clever. You need to be able to spot this. Actually, like is a very good insight coming from the literature. Now, what we're going to start with to identify this query Q in the top, we're going to look at this conditional difference of Y given Z equals 1 minus Y given Z equals 0. And in the first step, we're just going to use the consistency axiom to rewrite the Y outcome, right? So this is using the consistency axiom in the first step, which is right. This is well understood step, the consistency axiom. Then after this, what we can do, and this is actually an assumption that is coming from the graphical model. So based on some conditional independencies, in this case, exclusion restriction. So Y sub X and X sub Z, these potential outcomes are actually independent from Z. itself. So we can see this, derive this from the graphical model, or we can assume this, right, which is also commonly done. And then what that allows us to do, right, this z equals 1 and z equals 0 behind the bar can be removed. After this, we just need to rewrite this expression, right? So this is just reorganizing and rewriting this expression in a specific way. And then finally, what we can do is we can just use the law of total probability, right? So what we have here, we have a multiplication, right, of differences in potential outcome at x with differences in potential outcomes in y. And what we can distinguish, we can distinguish two cases, right? When x sub z1 minus x sub z0 equals 1, and when it equals minus 1, right? Because these are the only two cases where this random variable inside the brackets is non-zero. And what we can just use the law of total probability, right, to do this. And now is the crucial step in which monotonicity takes sort of becomes important. So what we can do is we can see that this second term under monotonicity is actually 0, right? Because x sub z1 minus x sub z0 can never be negative, because under the monotonicity assumption, we know that x sub z1 is always strictly greater than x sub z0, right? So what that allows us to do is to remove this term entirely. And now what is nice, we have our query here, right, in the right-hand side, and what we just need to do is we need to divide everything by this. So what this implies that we get a very nice identification expression, right, for the local average treatment effect in this specific setting when we use monotonicity through these steps, right? The key question for us is like, can we generalize this, right? Can we make this proof technique automated, and can we extend this to arbitrary counterfactual queries under monotonicity? And the answer is yes, which is very nice. So I'm going to talk about this next. Okay, so how do we make this into a general algorithmic approach, right? So what are the key ingredients, and how are we going to combine this to have a general algorithmic approach for identification under the monotonicity? So let's introduce some notation. So let W be a binary variable. T will be a set of monotonic parents of S. I'm going to say in a second what that means. And S is a set of non-monotonic parents of W. Okay, so graphically, this is exactly what is happening. So here S and T are possibly multidimensional. They don't have to be univariate. And what the plus here signifies, it encodes a monotonicity constraint, right? So in a graphical model, we would add a plus over an edge to encode a monotonicity constraint. Now, what the monotonicity constraint says is the following, right? So we are comparing two potential outcomes, W sub T comma S versus W sub T prime comma S, right? And what is important is that T and T prime, we're thinking of these two values as being ordered. So point-wise, T is actually smaller than T prime, okay? And what monotonicity means, the assumption is encoding that there's an inequality, right? Because T is smaller than T prime point-wise, we always know that the potential outcome with T is going to be smaller than the one with T prime, right? And what is important is this holds for every unit of the population, right? So U for us encodes a unit of the population, which you can think of as an individual, right? So this is what the monotonicity constraint is encoding algebraically, and this is how we're going to annotate this in the causal diagram with a plus. Now, what we can use, and here's the first sort of set of ideas of how to approach this, is we're going to develop so-called monotonicity reduction rules. Okay, and I'm going to explain exactly what the two monotonicity reduction rules are. One is called the simplification rule, and the second is called the difference rule. So they're giving here in terms of the algebra, which could be a bit I think hard to parse at first, but let's look at this. Actually, these rules are quite simple, and we're going to provide the intuition to understand exactly what these rules are trying to say. So let's look at simplification rules first. So there's two simplification rules, and let's look at the simplification rule number 1. Okay, so I'm going to give you the intuition for rule S1. So what we know under this monotonicity assumption, actually we know that if W sub T comma S is equal to 0, we know that this implies that W sub T comma S is also equal to 0. Okay, so this is some kind of a sandwiching of one of the potential outcomes based on the monotonicity constraint that we have, right? And what that allows us to do, if we go to the simplification rule number 1, so here y sub star is an arbitrary counterfactual, right? That has nothing to do, or doesn't have to have anything to do with W. And what we have here is we have a distribution over the joint outcomes, right? Joint counterfactuals outcomes, right? Now, using this implication here, what we can do is we can drop one of these terms from the probability term, right? So this rule will allow us to reduce this left-hand side to the right-hand side, right? And an analogous monotonicity constraint actually can be used in the same way for S2, right? So this is, you can think of this as a simplification rule of using monotonicity. Now, the second set of rules, what we call the difference rule, are very similar, but we're on top of using monotonicity, we're also just applying the law of total probability, right? So what we know is, we know that this term P of WT, S equals 1 and WT prime, S equals 0, that this is always 0, right? This is a direct implication, sort of implication of monotonicity. And by using this insight that this term is 0 and using the law of total probability, we can actually prove the two difference rules here, right? So what we're starting on the left-hand side with a clause which has a joint distribution over counterfactual outcomes, and we're using this difference rule to arrive at a difference of two things where this joint distribution over counterfactual outcomes disappears, okay? Which is very nice, right? So what these rules allow us to do, they allow us to go from the joint over counterfactual outcomes, which is very, very hard to identify, right, in general in causal inference, and what we end up with is a no joint, right? So this is in some sense the dream, right? So we're reducing these expressions into something that is more easily identifiable. Now, what is very nice is that actually these monotonicity reduction rules, they interplay very nicely with the general machinery for counterfactual identification. I will not go over all of the details in this. I will give you like a high-level summary of how counterfactual identification works. So what we begin with, a query queue, and what I'm going to look at a specific query that is directly related to local average treatment effects, right? So let's assume that Y is actually binary. For simplicity, it doesn't have to be, but let's assume this, and what we're trying to understand is we're trying to compute the probability of Y sub x1 being equal to 1 and comma the unit being a complier, right? And what we start with in this general algorithmic approach, there's a first step that is related to query cleaning. So there's a lot that you can read about this in some other papers coming from the Causal AI lab, or some previous papers as well. But in our case, actually, query cleaning is void. We don't really need to perform any query cleaning. Now, in the second step, what we can do is we can actually use the monotonicity reduction lemma on this term that we have, right? So what that's going to give us, we're actually going to break down this term that looks quite difficult into two terms, right? One is the probability of Y sub x1 being equal to 1, comma x sub z1 being equal to 1, and the second term is the same, but x has a subscript of z0, right? So if you go back to the previous slide, we're using the difference rule in this specific step, right? In this monotonicity reduction lemma. Now, what is very nice is that actually after this step, we've used monotonicity. After this step, essentially, we're following exactly the same steps of the general identification machinery for counterfactuals. So I'm going to just tell you what these steps are. So after this, what we really need to do is we need to take our graph, we need to look at the C components, we need to do the step of so-called counterfactual factorization. So after this step, actually our queries of interest look slightly differently. And then in the final step, we're actually just trying to send these queries into this identify routine that I'm not going to explain in detail, but this is one of the routines that appears in this 2002 paper from Tian and Pearl, in which they do algorithmic identification of interventional quantities, essentially, right? So these are the steps, and you can actually see in our example how this is reduced. And what we end up with, we either end up in this algorithm with an identification expression or a fail clause, right? That the query cannot be identified. Okay, good. So this is the identification expression that we get. In the end, you can all, of course, see that this is exactly the same result that we get with late. But now what is really nice for us is that this machinery can pick an arbitrary query, right? We don't need to have an IV graph. We can have different graphs. And the second question, right, that I want to talk about briefly in this talk is, are there other interesting queries that we could be using this method for, right? And I want to give you an example. So we're trying to find examples that would appeal to people in the econometrics literature, because they're very interested about using monotonicity in general. So actually, we've looked at this data set, which is called the 401k data set, which is I think very popular in the econ literature. It is used, I think, in some of these seminal papers of applying late. For example, Abadi 2003, I think, uses exactly the same data set. So we're asking a slightly different question. So what we're asking is, what is the local average treatment effect of 401k enrollment, which is going to be labeled X, on total total wealth Y for different income groups W, and we're conditioning on the group of compliers. Now, what the query looks like? So this is some kind of this is the local average treatment effect, right, that we saw previously. We're conditioning on compliers, but we're also conditioning on the income group. Now, let's look at a graph. We're proposing a graph for the specific setting, which is actually quite interesting and nice. So let's look a bit about what's going on. So Z is meant to serve as an instrument for a 1K enrollment, and Y is the outcome of interest that we're looking at. Now, what we can see in this setting is actually a lot of the assumptions from the typical late setting are violated, right? So for example, Z is pointing to Y, right? We're allowing the edge from Z to Y. So exclusion restriction is in some sense broken, right? Well, we have a monotonicity constraint between Z and X. This is crucial for us. So this stays the same. But what you can see as well is there are different types of confounding, which we think possibly makes sense, right? So occupation could be confounding for a 1K eligibility, income and total wealth, whereas savings proclivity could confound the relationship of enrollment to 401K and the person's assets, right? So what is very interesting is that in this specific setting, if we're using the traditional set of tools, we can just give up, right? So if we just try to use late and apply late here, the query is non-ID, right? The setting doesn't satisfy the assumptions, right, that we want. Now, what is very nice is if we actually plug this setting into the algorithmic approach, we can actually get an identification expression, right? So this setting is ID. And if you think about how it's not super complex, but if you think about the number of violations of different assumptions compared to late in terms of confounding, in terms of exclusion restriction, actually it's very interesting that this setting is identifiable, right? And what we've done is we actually studied this sort of empirically to see what we can get. And one of the findings that we have is that so what we did is we wanted to have a ground truth, right, to be able to make a specific claim about this. So what we do is we construct a structural causal model which matches the observational distribution of the data set in some sense, right? So this is step number one. And then what we're doing is now that we have the ground truth, we can estimate this conditional local average treatment effect, right? So we can even sort of compute it exactly from the structural causal model. We can use our identification expression. And what we did, just for interest of people familiar with late type of methods, we compared other late type of methods that exist in the literature, right? So there are some extensions of local average treatment effects in the literature, but what you can see here, these methods are, for example, in blue and orange. What you can see is that none of these methods actually capture the ground truth, which is given in red, right? So what this shows is this, in this specific data set, actually none of the methods that we tried, none of them can get the correct answer, whereas the new method that we propose actually can get this. And of course, we want to mention there's like a lot of other settings and different variations of graphs that would probably be interesting in studying, right? And so this is one very interesting example that I want to mention. And then after this, I want to mention another sort of complete class of problems in which monotonicity happens. This actually is related to my work in fair machine learning, and actually Razi, I think one of the organizers, has worked on this topic as well. So it's interesting that if we actually place monotonicity assumptions on different edges, right? So here, what we're trying to understand, we want to know about what would happen counterfactually. For example, if we manipulated a person's sex, how would for example, how would that affect their income? And the mediator in this case, M, is something like educational level, for example, an indicator 0, 1, whether the person has a PhD. And what we can show actually, and I'm not going to go into the details in the interest of time, what we can show in this setting actually is that these monotonicity constraints can actually help us identify some conditional queries. For example, we could be interested in the conditional total effect of X on Y, which is sort of interesting for people studying fairness. We can look at this conditional on the education level, right? So what is specific about this case? The specific thing is that we're conditioning on post-treatment variables, which in general, this cannot be done, right? So conditioning on post-treatment variables is almost always non-identifiable, but under these monotonicity constraints, using our algorithm, we can actually get the ID expression, right, in a completely different context. What I will mention in passing is probabilities of causation, such as probabilities of sufficiency and necessity, also fall under this umbrella, and our method is able to capture these. So just to conclude, so this is the second example that I want to mention, just to conclude and to say why we think this is important. So in this work, what we show is that we can develop develop a sound algorithm for incorporating shape constraints such as monotonicity, and this can be incorporated in the general machinery for counterfactual estimation, which is really great. What I want to mention, and I want to bring up this quote, and I want to sort of be dancing around this potential outcomes versus graphical models debate. So I'm bringing a quote from Professor Imbens, who in his 2020 paper discusses differences between PO and graphical approaches to causality, and he argues that models used in econometrics use economic theory more deeply than the current DAGs, exploiting monotonicity and other shape restrictions, as well as other implications of the theory that are not easily incorporated in DAGs and the attendant do calculus, despite the claim of the universality of DAGs, right? So in this work, we actually show evidence contrary to this claim, right? So we can refute this claim based on our work, and we provide the most general approach so far for encoding and leveraging monotonicity, which is very, very nice. And just to conclude, actually, with this, it seems that the graphical approach has had a lot of success in the non-parametric setting. In the linear setting that I mentioned, and now we are starting to add shape constraints to this as well. So this concludes my talk, and I'm happy to take any questions about this. And thanks for the time.
So thank you for the talk, Drago. There was already a few questions. There was a few questions, I think, from the same person in the Q&A. And I think they were related to some question on the slide 5, if we understand correctly. So if you don't mind sharing it again. There were some clarification questions.
You are muted, Drago.
Oh, okay, I thought I was muted. Okay, good.
Drago, you are muted.
Drago, you're muted.
Yeah, sorry. So let me just reshare. Let me reshare the slide. I think there's a typo.
Yes.
I think I need to flip in S1. I think I need to flip. I think someone is pointing to flip.
Yes, I think somebody was pointing you out at this. So
this is 100%
somebody.
It is.
Yes.
I think it's a typo. I think it's a typo, but I don't think things collapse after we fix the typo. I think the claims are.
Okay, then let's do it like this. This is good, and maybe this one, I think, if you want, you can answer also later. You can write in the Q&A chat if you want. If you want to double check, with a bit of calm. And another person also asked, would there be any difference if the approach would be nonlinear?
Yes. So this is an important clarification. So the approach that we have here actually is completely nonlinear. So we're not assuming linearity. We're only assuming monotonicity. So going back to the spectrum here of identification, so what we have is right, the non-parametric setting and the linear Gaussian setting. And we're somewhere in between, right? We're not placing assumptions on the functional form. We're only assuming monotonicity along these specific edges. So the approach is, what is really required is, and we do try to relax some of these things in the paper, and you can read how to relax these. But currently, for the main set of results, W and T need to be binary variables, right? So the elements of T need to be binary and W needs to be binary, because this is like for these binary settings, it's very easy to say what monotonicity is and how to define monotonicity. Moving beyond the binary case becomes more subtle. I think we can do it. But it requires a bit more work. Yes.
Okay. I think Razi has a question.
Yes, please.
Thank you, Drago, for the great talk. So I was just wondering if you could say a little bit more about like the generality of the query that you're identifying. So as far as I understand, so you're interested in some effects or conditional effects among the compliers, but they're also like under these assumptions effect among like other principal stratum could also be identified. And I was wondering like how general.
Yeah, so it's fully general. Actually, to be honest, we actually think the algorithm is complete. We don't have the proof yet, and I can make comments offline about why completeness is in this specific setting difficult. But we actually think that we believe that the algorithm is actually complete. So it is fully general. So in some sense, if you get a fail, it actually most likely means that the query is not identifiable. So to go back to your specific question, you could put any other principal stratum inside, and the method would work equally well in principle. So there's the generalities, I think, and conditional queries are acceptable. So in reality, anything goes in reality. There's no restriction. I think these monotonicity and some kind of binary variables along these at the start and the end of these monotonic edges, this is actually where the assumptions restrictions are in some sense, but we can relax even these, and this is done in the appendix of our paper.
Thanks. That's great. Just a quick follow-up. So like what complicates like the proof of completeness for you?
Of course, I can be very specific. So if, and I'm sure you're familiar with this literature, but essentially what we do believe what we can sort of prove is we can prove that the reduction from the query that you start with into layer 2, so to an interventional query, we believe that this reduction is complete, and we don't think that this is super difficult to prove. Now, what is funny is that we don't have a very easy way of saying that monotonicity could not help with identifying layer 2 queries. And we don't think that is the case, but it's not easy to prove, right? That we cannot come up with a query that monotonicity would in principle not be able to help. So in some sense, you can think about 2 steps, like completeness of the L3, so layer 3 counterfactual to interventional reduction, which we do think is complete and we can show. And then the second step is, can monotonicity help in identifying interventional queries? We believe the answer is no, but proving is no trivial. If you have the proof, we are very happy to talk about this.
Wonderful. Thank you.
Thanks.
Sounds good. Then let's move to Daiqi. So,
sorry, let me
thank you to Drago, obviously. Yeah.
Okay. So today I'm going to talk about 2 of my projects, which both leverages causality in online reinforcement learning for digital interventions. These projects are joint work with Xinyu, Ziping, and Lu Tong, who are postdocs and interns in our lab, and Peja, who's a professor at the University of Michigan, and my postdoc advisor, Professor Susan Murphy. First, let me introduce the scientific program that we are working on. On the high level, our overarching goal is to help users with cardiovascular disease to recover from their recent health crisis. Cardiovascular disease is the major cause of death worldwide, but most of it can be attributable to low levels of health-promoting behaviors. Cardiac rehabilitation is a supervised program where experts help the patients to form a healthy and balanced lifestyle after their cardiovascular events. And it is shown that this can be effective at reducing the behavioral risks or mortality for cardiovascular disease. But when the program ends, the outside support from the experts disappears, and the heart-healthy lifestyle and benefits for health starts to decline. This is when mobile health could be used to help the users sustain the lifestyle change that they acquired during the CR program. Mobile health uses mobile devices to monitor and manage patients' health through digital interventions. They are generally accessible and scalable, and they can provide ongoing support for users in their everyday life. In this specific work, we want to use mobile health to help users increase and maintain their physical activity levels. So Heart Steps is such a digital intervention that focuses on physical activity. There are multiple digital multiple components of digital interventions, including like message of the day, weekly goal setting, and anti-sedentary suggestions or walking suggestions. Anti-sedentary suggestions prompts the users to stand up and move around briefly for like 1 minute. And the algorithm is run every 5 minutes to detect whether a user has been sedentary for a while. Walking suggestions, on the contrary, encourage the users to engage in short bouts of physical activity, like a 10-minute walk. And there are 5 predefined but user-specific decision times where we can choose whether to send the walking suggestion or not. Such suggestions should be tailored to the evolving needs of the users. So we hope to intervene when the users are most receptive, but do not want to intervene too much to disturb the users. The contents of such suggestions are rule-based and tailored to the current context. And our lab specifically wants to find the best timing of sending the notifications. Specifically, at each of the 5 decision times, we decide whether to send the notification based on the current context, like whether a user is already exercising or not. So such a policy can handle the heterogeneity within a user across time. But to handle the heterogeneity across users, we need to develop a personalized policy for each user. And that's why we need to use online reinforcement learning to sequentially update the personalized policy based on the accumulating data of each specific user. So intuitively speaking, online RL continuously update the personalized policy by interacting with the users and learn from the user's behavior. In the examples of hard steps, the state can be the prior 30-minute step count, yesterday's step count, etc. And the RL algorithm will, based on the state, decide whether to send a walking suggestion or not. The user may or may not be receptive to the intervention in this current state, and such signal is reflected in the proximal outcome defined as the post 30-minute step count. The new state action and proximal outcome will be given back to the RL algorithm to update the personalized policy. So in the previous implementations of hard steps, the reward using the RL algorithm is just the short-term step count. But remember that the health outcome that we want to achieve is the long-term behavior change. But such health outcome is too distal to be used in the RL algorithm for policy update. So that's why in this new clinical trial, we choose to use an intermediate outcome that is closer to the health outcome, but is also efficient for policy learning. Our scientific team defines the reward as the commitment to physical activity, and such commitment to PA is a strong predictor of the health outcome. On the other side, we know that the walking suggestions directly target immediately actionable tasks, like a 10-minute walk. So the walking suggestion will likely increase the short-term step count, but if the users are receptive to the interventions, they will keep their regular exercises every day, and it's likely that their commitment to physical activity will be increased. So that's why we expect the proximal outcome to be a mediator between the intervention and the reward. Such reward can be measured through surveys where a user self-report their feelings about physical activities. So in general, mobile health problems, users' behavior are really noisy because people's everyday life is just noisy. And even if we use some intermediate outcome like commitment to physical activity, such reward can be sparse, like we can at most obtain 1 reward per day. So both of these require a significant amount of data to learn a policy. But we always have limited user-specific data in mobile health, because, for example, a user might just stay in the trial for 3 months, and then there are at most 90 rewards in total. And this problem is specifically severe when the user just joined the trial. So that's why we try to embed the behavioral theory in the causal directed cyclic graph. This causal DAG represents the strongest causal relations among all, and the absence of an edge represents our assumptions of causal relations that are weak or does not exist. Then the conditional independencies implied by the causal DAG will be used as the assumptions in the RL algorithm. The misspecified assumptions might increase the bias, but we expect that using such domain knowledge will help us to significantly reduce the learning variance. And also we will use the previous data to construct the prior inhibition methods to warm start the algorithm. So jointly we use the causal DAG and the previous data to improve sample efficiency, meaning that we will be able to learn a better personalized policy with the same amount of data. Now let's go back to the example of hard steps. This causal DAG shows 1 day of user in hard steps. There are 5 decision times per day. Each action is whether to send a walking suggestion or not. And the context can include the prior 30-minute step count, yesterday's step count, etc. The proximal outcome M is the post 30-minute step count. And there are 2 variables that are slowly evolving over time, but are the key factors that can capture that can be predictable of the long-term behavior change. The first one is the reward, defined as the daily commitment to physical activity. And as we mentioned before, the walking suggestions directly target the short-term mediators, but increased mediators will jointly increase the reward commitment to PA. And another slowly evolving variable is the engagement. If we send too many notifications, the users will just disengage from the interventions, and this decreased engagement will decrease their adherence to the interventions, which will further reduce the reward. So basically, we expect the positive effects of the walking suggestions to go through the step counts, but expect the negative effects of the interventions to go through the engagement. And the reward and engagement of the previous day and the current context may jointly affect the receptiveness to the interventions and such the proximal outcome M. Okay, so now let's talk about how to use causal DAG for state construction and reward design in RL algorithms. Notice that in this example of hard steps, there is actually a bag structure. So each bag represents a day and contains 5 decision times, but there is only one reward at the end of the bag. We denote the bottleneck variables that separates the past bags from the current bag as B tilde. And in this example, these bottleneck variables are RT and ET. We assume that given the bottleneck variables and fixed values of the actions, the distributions of all the variables in the DAG is stationary across bags. So basically, it means that we put no assumption in the variables within a bag, but we assume that the same bag structure will repeat over time. Our goal is to maximize the cumulative reward, and the reward is bag-specific reward, given some discount factor gamma bar. Notice that here the transitions are non-Markovian because 5 actions jointly impact one reward at the end of the bag. Besides, the transitions are also non-stationary because, for example, if we're choosing the last action in a bag, we can use the previous actions and mediators to construct the policy. But when we choose the first action in a bag, we cannot use the later actions to construct the policy. So like there's non-stationarity within a bag. Therefore, this problem is not a standard Markov decision process. But utilizing the assumption that the same bag structure is repeated over time, we can notice that there is actually a periodic structure here. So that's why we try to fit it into a periodic Markov decision process. Intuitively speaking, periodic MDP allows non-stationarity within a period. So all the state space, action space, reward, discount factor, and transitional reward functions can all depend on the time index within a period. But the same structure for a period will repeat over time. Now, to transform the problem of bag decision times to a periodic MDP, we notice that the actions have already been defined naturally, and we will discuss how to construct the states later. Then, and the first K-1 instantaneous rewards are actually 0 because we do not observe the daily commitment to PA just after choosing the first action. And the last instantaneous reward is the bag-specific reward. Similarly, the first K-1 discount factor is 1, but the last discount factor is the bag-specific discount factor. In this way, we will be able to recover the value function needed for the bag decision times problem. And the value function is defined as the cumulative reward given the current state. So if we are able to identify a policy pi that maximizes the value function for every state, then we will be able to achieve our goal of maximizing the expectation of cumulative reward overall. Now let's discuss how to construct the states in this problem. Note that to fit into the framework of a periodic MDP, the state transition need to be Markovian. And this will be achieved by reading the conditional independencies from a DAG. Specifically, we define a dynamical Bayesian sufficient statistic such that given the sufficient statistic and the action, all the previous rewards are independent of the history. So intuitively, it means that a sufficient statistic is the boundary of the observed history that separates the history from all the future rewards. And it is guaranteed that a sufficient statistic will have Markov state transitions. In this hard steps example, suppose we are choosing the last action in a bag, then the state can be used as the reward and engagement in the last bag, the mediator and action in the current bag but previous time points, and the current context C. Another sufficient statistic could also include the previous contexts. However, notice that the sufficient statistic is not the only one that guarantees Markov transitions. There are also other states that have Markov transitions. For example, if we substitute the mediator in state S with the previous context, then the state S hat also have Markov transitions. In fact, all the previously defined 3 states have Markov transitions within and across bags. And although their state transition is non-stationary within a bag, it's generally stationary across bags. So actually all of them can fit into the framework of a periodic MDP. Then which state is the best? In fact, we proved that the optimal value function based on a D-bus is no less than the optimal value function based on a non-D-bus. So this means that in all the distributions compatible with the DAG, a D-bus always generates the maximal optimal value function. So like it will have the maximal cumulative rewards, but this does not hold true for a non-D-bus. And in this example of hard steps, the inequality strictly holds when, for example, 2 different values of the mediator correspond to different optimal actions. So if we use the mediator to choose the action, we will know which action to choose based on specific values of the mediators. But if we only use the context C to choose the action, then we can only choose it based on the conditional distribution of M given the C. And the takeaway here is that when we design a clinical trial, it is helpful to identify the mediators of previous actions that could potentially help us construct a better personalized policy. And another aspect to compare the states is the learning variance, because both the sufficient statistics yield the maximal optimal value function. This happens when we have infinite amount of data to actually learn the true optimal policy. But during the learning process, we only have finite samples. Then the sufficient statistic with a smaller dimension will have a smaller learning variance. Because in this example, we know that given other variables in S-check, actually the previous context C are independent of the future rewards. So in the true optimal policy, the coefficients for this context C are actually 0. Then when we have finite samples, it's not sample efficient to learn this 0 coefficients if we already know the conditional independency implied by the DAG. Okay, so based on the previously defined state, action, and rewards, we will be able to form an RL algorithm. But due to the time limits, I will only go over the high-level idea of this algorithm. So we adapt algorithm called randomized least squares value iteration to the problem with backed decision times. RLSVI is a Bayesian method that handles the exploration-exploitation trade-off in RL by sampling from the posterior distribution of the policy parameters. Remember that Q function is the cumulative rewards given the current state and action. And the Bellman optimality equations describes the relationship between the optimal Q functions And here, this Bellman optimality equations are specifically for the problem with back decision times. Then we model the Q function as a linear function in the basis functions phi. The basis function phi can be flexible to capture any nonlinearity. And then using the Bellman optimality equations, we can estimate the Q star and then fit a Bayesian linear regression of the estimate of Q star on the basis functions. Then an estimate of the parameter beta is the draw from the posterior distribution of beta. And then the optimal action will be the one that maximizes the estimate of Q star based on the specific value of beta tilde. Here we want to draw beta tilde from the posterior distribution because this has been proven to be an efficient way of exploration in RL. In the end, in the clinical trial, we will compare the personalized policy learned online with a randomized policy, which always send an intervention with a fixed probability. And this trial will go into the field next year. But before that, we need to verify that our proposed algorithm is working as expected on a simulation testbed. This simulation testbed is constructed using previous hard steps data based on the causal model in this DAG. And it provides an estimate of counterfactual outcomes. So we will be able to evaluate the cumulative rewards for a policy that might be different from the policy used to collect the previous data. We do not know what the users will be like after the trial actually starts. So what we can do is to create different variants of the testbed that actually represents different possibilities of the users in the new trial. And we want to verify that our proposed algorithm with the same hyperparameters works well across all the testbed variants. So it's stable for different possibilities of users. So in addition to the vanilla testbed, which is directly constructed from the data, we also adjust the positive effect that goes through the step counts and the negative effect that goes through the engagement to create different variants of the testbed. And we can see that our proposed algorithm, the backed RLSVI, is always one of the optimal algorithms across different variants. And the baseline algorithms the baseline algorithms are able to capture the positive effects, but they fail to capture the delayed negative effect reflected in the disengagement. And although in general, we want to trust the behavioral theory embedded in the DAG, we also want to be robust to mild misspecifications of the assumptions in the DAG. So we also create the different variants that add different edges to the DAG to represent different variants of the testbed. For example, when here shows two variants when the contexts are not exogenous or when the mediators are misspecified. And we can also see that the proposed algorithm is stable across the variants. So for state construction, we use the causal DAG to construct the states that guarantees Markov state transition while ensuring that it has the maximal optimal value function and minimal learning variance. And then I will briefly introduce how to use the causal DAG for reward design. For reward design, we start from a very simple case of online contextual bandit, which means that previous actions do not affect the future states. Instead of optimizing the original reward in the algorithm, we optimize a surrogate reward, R tilde, defined as the conditional expectation of the original reward, given the mediator and the state. The intuition is as follows. A surrogacy assumption assumes that there's no direct effect from the action to the reward. So given the mediator and the state, the reward is independent of the action. When the surrogacy assumption holds, the expectation of the surrogate reward is the same as the expectation of the original reward, but the variance of the surrogate reward is smaller. And we still have this advantage even if the reward is learned online, because we can pull across different actions to estimate the surrogate reward, since the surrogate reward do not depend on the action. But in a standard contextual bandit, we need to learn the average reward of each different action. So pulling across different actions will increase the sample efficiency. So we use a reward design agent, which use previous data to learn the surrogate reward. And then the surrogate reward will be fed into a bandit oracle, which chooses an action based on the current state. Then the new information will be given to the reward design agent to update the surrogate reward online. A regret is a measure of the difference between the cumulative rewards given the true optimal actions and the actions we choose. We were able to prove that when all the causal models are linear, optimizing the surrogate reward has a lower regret under this condition. And this condition means that if the dimension of the mediator is relatively small compared to the dimension of the state, then there's a larger advantage of pulling across actions to estimate the surrogate reward. And here we also allow mild violation of the surrogacy assumption, which is quantified through the E here as the surrogate error. Okay, I will skip the simulation results due to time limit, but okay, so let's provide a summary. We use the causal DAG for state construction in problem with back the decision times. The causal DAG helps us recognize the back structure and its connection with a periodic MDP. Based on the causal DAG, we construct the state that has Markov state transitions within and across backs. Besides, it helps us recognize the sufficient statistic of the history with the smallest dimension so that we can guarantee the maximal optimal value function and minimal learning variance. When we use it for reward design, we construct a surrogate reward with the mediators, and the surrogate reward is updated online. Using the surrogate reward in learning will reduce the variance and also increase sample efficiency. Here are the QR codes for the 2 papers that I mentioned in the talk, and that's all for my talk. Thank you.
Fantastic. Thank you, Daiqi. So there are some questions in the Q&A. I think maybe one of them you kind of already answered, but just to be sure, I'll ask you a bit. So the first question is, what do you lose from collecting the period action or intermediate variables into one period? So the action would be, for example, the sum of actions or the average during the period. So what do you lose from this?
Okay, so that's a good question. So like an alternative is to treat all the actions in a bag as an action vector, right? But in that way, we can only choose it at the beginning of the bag, and we cannot use the real-time information like the context when we choose these actions. And actually, that's one of the baselines that we use in our simulation, where we choose all the actions as a vector and choose it at the beginning of the bag.
Okay, nice. And then there is another question, which is a bit more general, I think. What kind of basis functions phi could you include?
So in our simulation, we use the basically a linear function, which only include the state and the interaction between the action and the state. And also to increase the sample efficiency, we actually pulled across different time points to estimate the main effect of the state. Because otherwise, since there are many decision times in a bag, we need multiple parameters to estimate that, but we only have limited data. So that's what we used. Yeah, it's basically a consideration of the sample efficiency here. But if we want to want it to be flexible to capture the nonlinearity, other basis functions like Gaussian kernels or other kernels could also be used.
Okay, sounds good.
Thank you.
Great. Thank you, Drago and Daiqi, for your wonderful contributions. We are also right on time. That rarely happens. So let me just share my screen to wrap up by sharing information about next week's talk. So for next week, we will have Angela Zhao from University of Southern California talking about robust weighted Q evaluation and iterations under sequentially exogenous and unobserved confounders. And we will have Qingyuan Zhao from University of Cambridge as the discussant. So hope to see you all next week.
Thanks for the time and
Sounds
the
good.
invitation.